Good day, everyone. Here's the spreadsheet that I've shared with the class, which actually allows us to do simple calculations on a simplified model of a power system. So shown here on the left side is a model for a generator. And then we normally step up the voltage of a generator through a step-up transformer here. And then power will flow through a transmission line, modeled as a resistor here. At the end of the transmission line is another substation where we step down the voltage. Eventually, from the step down voltage, where we connect the load. So typical power flow goes from the generator up the transformer, through transmission line, down to step down transformer, and then to the load. So that's the typical power flow as shown by these current directions here. However, in doing some calculations or basic analysis, we typically start from the load side here, and then we walk our way backwards to the source. And that's what we're going to show in this calculator. So for this calculator, the rule is you can play around with the green cells here. So you can type values with the green cells, and you can type values with the gray cells. So green and gray are editable. Orange and yellow are not editable. Okay? So orange is simply a copied value. Yellow is an equation or a function cell. So let's try this. So this green here, a gray here shows the turns ratio for the primary of the T1 and then the secondary of T1. So we picked here 30 to 230. The typical transformation is from a 13 kV to a 230 kV transformation. The resistance of the line here, you can type values there. I typed a 1 ohm resistance. You can change that next time. If this is a 230 kilovolt side, then this must be a 230 kilovolt side, so you don't change this. This is a copied value from this. But this you can change here. It's gray. You can pick a voltage level for the secondary of this transformer. We pick right now a 34 kilovolt rating for the secondary of the second transformer. So what we're saying here is any voltage here will be transformed to this side here, normally from low to high. And then this one is a high voltage side, transform high to low. And this one is another lower voltage side compared with the transformer, a transmission line, sorry. Likewise, for the load, we can play around with the gray values. Right now, we've set a 1,500 watt load with a power factor of 0.7 power factor lagging. This sheet here is for a load with a lagging power factor. There's another sheet there for a leading power factor. So we don't change these units here and this notation here. What you'll notice is for the load, we need to specify the power requirement, watts, power factor, and the voltage. The voltage here is copied from the rating of the transformer. So basically, you connect a load consistent with the rating of the transformer. If this one is a 34 kilovolt load, then that transformer, then this should be a 34 kilovolt load as well. So the reactive power here is computed from the power and the power factor. The volt ampere is computed as well, again, from the real power and the reactive power. And then the current here is computed in polar form, magnitude and angle, based on the voltage here and the power here and the power factor and the reactive power. So quickly, let me change one value here. Suppose I want a 2,000 kilowatt load. at the 2000 watt load, then all the values here have changed, Q have changed, VA changed, the current has changed as well. So if I increase the power factor closer to 1, perhaps 0.9, notice that the reactive power reduced significantly, the volt ampere reduced as well, and then the current reduced as well. Notice that the angle here follows strongly with the power factor that you've picked here. If I pick a 0.95 power factor, I now have a smaller angle here. Again, it's negative because the load, the current lags the voltage, which is set at 0 degrees. So step 1, you can play around with this set here, change the power requirement, change the power factor, and observe how the reactive power changes, the volt ampere, the apparent power changes, the current, both magnitude and angle changes. And basically that's it. So if you play around with this, you can now observe how current is delivered here. So this current here flowing through the load is copied from this one here. So this one are copied version of this. The voltage here is copied version of that. So basically the voltage of the load is the voltage of the transformer low side here. The current here on the line are calculated values. The angle is copied, but the current here is computed based on the turns ratio here. So you compute the current on the transmission line here. Notice that this is the high side, that's the low side. So the current now goes scaled down on the high side. So this one is scaled to this one based on the turns ratio that we have here. Because of the current there, you can now compute for the power loss, which is simply equal to the I squared times the resistance there. If you want to change the resistance, suppose you have a larger resistance for your transmission line, then it's the power here that will change. Currently there won't change, the power here will change. This current here is computed from the load current and not from what's coming from the source here. So even if you change the resistance here, that current there will not change. So from this loop here, we can write a loop equation. We call it a Kirchhoff's voltage law equation. So the voltage here is equal to the voltage here plus the voltage here. So the voltage here comes from the voltage here. You step it up from 34 to 230 volts based on the turns ratio there. So that's what we have there. The voltage drop here can be computed from the current and the resistance there. So this voltage here is actually equal to the voltage here plus the voltage there, and this is the voltage across here. So we computed it's 248.09. So notice that if we increase the voltage, the resistance here, 5, we expect what we expect to happen here, the voltage will increase accordingly. You have fixed voltage here, larger voltage drop there, you get a larger voltage at the source side here. Put it back to 1 ohm, so that's the voltage there. You know the voltage here, you now transform this voltage to the low side of the generator step-up transformer. So the angle there is copied from there. The magnitude of the voltage is based on the turns ratio there and the voltage at the high side. The current here, likewise, is a transformed version of the current here. So that's the current there through this line. We copy the angle there, but the magnitude of the current is from this one scaled based on the turns ratio of the transformer here. This is the low side, so we expect higher current on the low side of the transformer. So that's a higher current there compared with the current on the high side. So that's the current, and that's the magnitude, and that's the angle there. This generator here will simply have the same, exactly same voltage as the transformer here. So we copy the voltage there, we copy the angle there. So this now is the voltage at the source. So basically that's it. It's a very simple calculator. You play around with the value of the load and you observe how the voltages and the currents will change accordingly. Actually, here's the voltage that will change accordingly. All these are copied voltages. Okay. Then eventually the voltage at the source will change accordingly based on the voltage here. You can also play around with the resistance here. If you have higher resistance, then you have higher losses there. Likewise, if you have higher currents here, then the current there increases as well. You have higher losses here as well. So basically, this just illustrates how the losses varies with the resistance and with the current flowing through the transmission line. Again, if you have a question on this sheet here, you can post on the corresponding forum. The second sheet here is this time for a leading power factor. The first one was a lagging power factor. This time it's a leading power factor, so you can try this out as well. The third is more interesting actually. So we assume a lagging power factor for the load, but we add a capacitor in parallel to the load. Okay? And the key here is basically, if you pick a load here with a low power factor, suppose we have a 0.05 power factor there, then this is the requirement Q. This load here requires this much Q, reactive power. But what we recommend to do is you provide a capacitor that will provide that reactive power there. If there is no reactive power here provided, then that will be the current drawn by the load there. It's the current drawn by the load there. But as soon as we provide reactive power here, I'll use a negative value, that's the convention, and I will try to meet some of this requirement. You suppose a 1,300 VAR is provided by the load, by the capacitor there to the load. So that will basically provide for the current here, and supposedly the current here will change. There you go. So that's the combined current there for the load and the capacitor. So that's a 15 ampere current now from previously 2000 ampere current there. So this now is the parameter for the combination of the load and the capacitor. And that will be drawn here and eventually will be converted to this other side here of the transformer. So that's basically what this third sheet shows, how current is reduced by this capacitor compensating for the requirement of this load. So basically that's it. If you have a question, you can send me an email or post in the corresponding forum.